Tucson, Arizona, the soul of the Sonora Desert. This beautiful area is known for cactus, colorful sunset, and sunny days. But temperatures can be extreme, with summer highs up to 118 degrees Fahrenheit. Tucson Electric Power, or TEP, is the electric utility that provides safe and reliable power to the city of Tucson and surrounding areas, ensuring the safety of million residents from the heat while delivering the energy needed for a modern American life. Currently, TEP's generation mix consists of 50% natural gas, 35% coal, and 15% renewable energy, but they are actively working to transition to cleaner sources. TEP is committed to reducing the environmental impact of its emissions by setting aggressive goals to retire all coal generation in the next decade and replace it with renewable resources.
However, with a projected 0.8% annual load increase and planned generation retirements, TEP is facing a resource generation gap of 1.8 gigawatts by 2050, presenting challenges that require careful planning and strategic solutions. In order to overcome these challenges, TEP delivers a biennial Integrated Resource Plan, or IRP, to ensure a reliable and affordable electrical system. IRPs plan all aspects of future electricity supply and demand while considering various system constraints, government mandates, and the complexity of integrating different types of generation onto the system.
I can see that,
Right.
yes.
All right, take it away. For 20 years, it was just a gradual improvement in nuclear, gas, and coal plants. So it was just a matter of like how big and exactly when you wanted to build those. And now things are so different. You have customers generating their own power or wanting to access their own power and just bypass the local utility. And you have new technologies, storage is new, and now you have energy storage in people's garage. And then you have EVs and electrification. So there's just so much going on at once, and over all that is climate change. And that's making it more difficult to generate the energy, and it's making it more difficult to know how much is going to be demanded. Mm-hmm. And those are the real challenges. It's technical and it's the climate.
Since TEP's last IRP was released in 2020, the world has experienced macroeconomic shocks that had a major impact on the utility, including the COVID pandemic, a solar panel anti-dumping case in the United States, and of course, the war in Ukraine, resulting in massive disruptions to the supply chains of renewable energy products. In addition, TEP faces known challenges around what the company calls heavy transmission constraints.
Then we do have this issue of limited transmission capacity into the area where you have the need. So in the case of Tucson, there's only so much upgrading you could perform on our transmission lines. But there are areas where we actually have new need, and there are real environmental concerns about siting new transmission construction in those areas. So those areas we call load pocket because there's a very limited possibility of siting new transmission. And even upgrading existing transmission goes through a very rigorous process. We have to go through the line siting committee that weighs environmental, economic, and social considerations of an upgrade to align. And then we have to make sure that it's economically viable, of course, not just for the citizenry, but for the company.
To address Tucson Electric Power resource planning challenges, we use our IRP project to explore solid oxide fuel cells as a potential solution to diversify TEP's energy generation mix and help avoid the transmission constraints that are being seen in the Tucson area. Fuel cells offer long-term stability and fuel flexibility while producing negligible air pollution due to no combustion. Their small footprint allows for closer insulation to the load, minimizing the need for new transmission projects and easy permit requirements, which could help TEP diversify its generation sources and mitigate load pockets and other transmission issues. Our IRP for Tucson Electric Power aims to compare alternative scenarios with fuel cell solution to determine the potential of solid oxide fuel cells as a viable, cost-effective, and environmentally friendly option for TEP in the pursuit of clean and reliable energy for their integrated resource plan. Tim and I researched the potential of fuel cell technology as a cost-effective emission reduction solution for Tucson Electric Power. We compared 3 scenarios. In the base case, we retire coal generation and introduce CCGT as a replacement. This aligns with TEP's objectives and a common practice among utilities with coal portfolios. We maintain a 15% renewable energy capacity without carbon constraints. In the high renewable case, we retire coal generation and significantly increase portions of the renewable sources like solar and wind. We also incorporate substantial battery storage capacity. An ambitious goal was to achieve 75% reduction in CO2 emissions compared to the base case projected emissions in 2050. The fuel cell case, involving retiring both coal and CT generation, we replaced the fuel cell generation considering TEP's transmission constraints. Our focus was to minimize the need for additional transmission infrastructure. Similarly to the high renewable case, our target was 75% reduction in CO2 emissions compared to the base case projected emissions for 2050. Starting with the base case, which is the brown line, we observe an initial CO2 emissions of 3.6 million metric tons, gradually increasing a little over 4 million metric tons. Moving on to the high renewable and fuel cell case, both aim to reduce emissions from the base case by 75%. This corresponds to the 1.01 million metric tons of CO2. We successfully achieved this reduction in both scenarios. Before we proceed, we like to stress the different types of emissions, where CO2 is a greenhouse gas emissions, but there are air pollutant emissions which are harmful to human health and can lead to premature death, like nitric oxide and sulfur dioxide. We highlight one of the benefits of the fuel cell scenario, emitting negligible NOx and SO2 air pollutants thanks to the absence of combustion process in the fuel cell technology. The monthly hourly emissions for NOx for each case reveals interesting findings. The base case had a higher NOx emission, primarily due to the presence of CCGT generation, which is known to generate air pollutants. However, we observe a notable difference between the high renewable and the fuel cell case. Despite the majority of renewables in the high renewable case, it is still emitting significant levels of NOx due to the CCGT in the generation mix. In contrast, the fuel cell case demonstrates negligible NOx emissions throughout the year, thanks to the absence of combustion in the fuel cell technology. Examining the workday shows greater quantities of NOx air pollutants emitted during that day due to CCGT being dispatched, more due to the lack of renewable sources that day. This is an advantage which allows TEP for strategic deployment closer to communities and customers without compromising air quality, bypassing transmission and permitting challenges that are being seen in the Tucson area. The capacity mix represents the total nameplate capacity of each generation type. In the base case, we projected the retirement of coal generation by 2040, with majority of the capacity being occupied by CCGT generation. The high renewable scenario showed a capacity that is more than double that of the base case, as it relies heavily on renewable sources such as solar and wind. In the fuel cell case scenario, the capacity mix is twice that of the base case and still has significant renewables added. However, it is 12% lower than the high renewable scenario as we prioritize the use of dispatchable fuel cells. For the generation mix, which represents the total energy produced for each generation type throughout the year, due to the relative low energy generated from renewable sources, there is no curtailment observed in the base case. In the high renewable case, where 80% of the energy generated is from renewable sources, there is a 24% curtailment observed throughout the year. This means that significant portions of energy generated from renewable is not utilized and goes unused. In the fuel cell case, the incorporation of the fuel cells as a dispatchable load allows for better integration of renewable energy into the system. By reducing the reliance on renewable energy, the curtailment is lowered to 12%. This indicates that a smaller percentage of renewable energy generated goes unused.
The monthly hour average graph provides useful insight into the dispatch capacity mix throughout the year. In all scenarios, renewable generation is prioritized and dispatched first due to its lower cost. When renewable generation exceeds the demand, excess energy charges the battery. This is represented by the light purple color. When the storage reaches full capacity, energy is curtailed. This is represented by the light gray color. Curtailment is more prevalent during the earlier and later parts of the year when loads are lower. The ideal scenario with minimal curtailment occurs during the summer and peak seasons, when excess renewable generation is mostly utilized to charge the storage system, resulting in lower curtailment. The high renewables case deploys CCGT as the dispatchable generation. However, in the fuel cell case, CCGT is replaced by fuel cell technology. We ran into a problem that is common in systems with high amounts of renewable energy, and we thought it would be interesting to highlight a resource planning challenge. In German, it's called Dunkelflaute, or dark doldrums. This occurs when capacity factors for renewable resources decrease below expected output. If this occurrence is not prepared for, the end result can be lost load and an inoperable system. This is the result of a bad week when capacity factors were particularly low, especially wind, which dropped to less than 10% in many hours. September 19th is a particularly bad wind day. We zoom in to look at the dispatch on this day. You can see where the real problem is low wind beginning around 11 a.m. and lasting throughout the day. The result is that batteries fail to sufficiently charge and are depleted by early evening. Meanwhile, wind remains almost non-existent. So no matter how much more renewable capacity we added to the system, the problem did not go away. To avoid lost load and an inoperable system, additional CCGT was added to the high renewable case just for these few hours during the year when the potential for Dunkelflaute was real. The fuel cell system did not have to be adjusted because there was already enough dispatchable fuel cells in the model to manage the doldrum issue in this case. The lowest cost scenario is the base case, with the required revenue of just over $2 billion in 2050. However, as we explained earlier, this scenario comes with a cost of much higher emissions and local air pollution. The high renewables scenario achieves very low emissions along with almost no change to average rates due to the comparatively low cost of renewables, which gain the additional advantage of federal tax incentives. The fuel cell case is the most expensive at just under $3 billion required revenue in 2050. This is due to two factors. First, even though fuel cells do qualify for federal tax credits under the Inflation Reduction Act, the capital cost of the equipment and installation is 3 times more than other generation alternatives. Second, by 2050, the fuel cells are using a significant amount of hydrogen, which is much more expensive than natural gas. We conducted a fuel sensitivity analysis, which considered the intersection between fuel mix, emissions, and the impact on rates. As hydrogen content increases, so does the average rate, but emissions are reduced. By 2050, the fuel cell case utilizes both a 50% hydrogen mix and pure hydrogen. However, due to cost considerations, the majority of dispatch is for the 50% hydrogen mix, which explains why the middle two bars are very close in rate and emissions. While the 100% hydrogen option in 2050 is the most expensive, the option is there for TEP in the future to have dispatchable, emissions-free generation. One theme consistently came up: the problem of a heavy transmission constraint. This is an issue that utilities all over the United States are dealing with, given the rapid incentivized growth of renewable resources. TEP has unique challenges given the limits of existing transmission upgrades, as well as the difficulty to build infrastructure on Indian reservations and other restricted lands. Our IRP aimed to ask the question if fuel cells, given their benefits and challenges, was a viable solution for TEP to help with this problem.
Our conclusion is that the large-scale deployment of fuel cell system as a sole dispatchable resource on TEP system is impractical and not recommended. What is recommended is to implement a smaller scale strategic deployment of fuel cells in the Tucson area.
Why? First, fuel cells enable localized generation near the load. Second, they circumvent the transmission problem while adding dispatchable generation to underserved loads. Third, fuel cells can help deliver on future net zero emissions requirements. Fourth, fuel cells add to TEP's generation diversity, which is a priority for the utility. And finally, Tucson is an attractive region for new business, such as server farms and mining operations. Fuel cells have the potential to help with Tucson's economic growth as a flexible option to quickly add generation capacity for new commercial or industrial businesses.